So this is going to be our unit on oscillations and simple harmonic motion, okay? So let's take a moment to define what exactly is harmonic motion. Harmonic motion is motion that occurs periodically, that occurs over and over again, that follows a certain path. For example, a car going around a racetrack, circular motion, is an example of harmonic motion. Because if I were to draw a racetrack, the car would be going around and around and around the racetrack, and it would continue to trace out the same path. In harmonic motion, we introduce variables like frequency and period that analyze things like how many times does our object trace out the path every second. That is frequency. Period would be how long does it take our object to trace out the path. So the characteristic of harmonic motion is you will always be finding yourself in the same place again, okay? But the characteristic example of simple harmonic motion is the example of the oscillator, specifically with the spring, okay? Where if I had a spring and I hung it from the ceiling right here and I attached a block of mass to it, if I were to pull this mass downward, and then I would pull it down to right about here, then I release it, then the spring would pull the mass back up, and the mass would have some momentum, so it would continue to accelerate upward, and the mass would compress the spring in its upward ascent, and the compressed spring would therefore release its compressed spring potential energy and force the mass back downward, and the mass would continuously oscillate up, down, up, down, up, down. And if we ignore air resistance, then this harmonic motion will continue forever, okay? You see, it traces out a path, up, down, up, down, up, down. Let's discuss the mathematics behind spring harmonic motion, okay? So let me draw us another example for our analysis. I have a spring connected to a wall, which is connected to a mass, and this is oscillating on a table that is smooth, okay? Now, it's important for us to understand here that very often on your FRQs, on your written responses, you will not be explicitly told on a plane with negligible friction. You are not going to be specifically told that there's no friction. It's going to say smooth surface, and you're going to have to, given that word, know that you should assume negligible friction. If they said rough surface, you should know to assume that there is friction, okay? Another assumption is that you should never assume that there is air resistance present unless you are explicitly told that there is air resistance. Another assumption is whenever you see the word string, whenever there are strings involved in your setups, you should always assume that those strings have zero mass, unless otherwise stated, okay? Anyway, let's get back to this. If I were to pull this block to the rightward direction, if I were to stretch out the spring would exert a restoring force onto the block and pull it back to its equilibrium position. Now that the mass has some kinetic energy, it will transfer that kinetic energy back to the spring by compressing it back in the compressed direction, and the compressed spring will then re-exert a force on the mass, and it will continue to oscillate left to right as such. Given this, we can take some of our equations and analyze this. We know that the force acting on this mass is equal to that mass times its acceleration, okay? But we also know that the force acting on this mass is the spring force, which is therefore equal to the spring constant of the spring times the displacement x in the negative direction. So this is an important derivation to keep in mind. This ma equals negative kx, okay? Now, given that this is the calculus course, we will be able to set up a differential equation using this. We have our mass, and what is acceleration? It's the second derivative of position with respect to time. Equals our negative kx, okay? Now we're going to come back to this derivation in just a moment after we introduce some of our equations that I alluded to previously, okay? We introduced quantities like frequency and period, okay? So period is how long does it take our object to complete one oscillation, to complete one journey through the motion, to leave from a point and return exactly to that point with those conditions, okay? So an example here would be as this is oscillating, okay? Let's say the mass starts at its maximum value on the right and it oscillates back down and then it comes back to its maximum value on the right. That would be one oscillation. Now be careful, because if, let's say, we define our starting point as the center, the equilibrium point, then as we're doing our oscillations we go one way and come back. However, we are not back to the way we started right now, because at the beginning we had an initial velocity to the left and now we have an initial velocity to the right. So in order to complete this oscillation, we need to go back to the right and then return to the middle to replicate the same conditions we started with. This would be one oscillation. So period is a quantity that tells us how long it takes our object to complete said oscillation. Therefore, it would be in units of seconds. Now, on your reference sheet with the equations for period and frequency, you're given that period equals 2 pi over omega, which we will discuss in just a moment, which equals 1 over frequency. Okay? So period is 1 over frequency. If I have a quantity that tells me how long it takes me to complete one oscillation, the reciprocal of that quantity would tell me how many oscillations are done in a given amount of time. Okay? So 1 over frequency basically asks how many oscillations per second. Therefore, its units would be seconds to the -1, or hertz, which we have probably heard of before. Now let's examine this quantity, omega. Omega, as we remember from rotation, is going to be angular velocity. Okay, but what does rotation or angular velocity have anything to do with this? Well, let me show you. Angular velocity is in units of radians per second. Okay? And if we know that there are 2 pi radians in a full circle, that means we need to traverse through 2 pi radians in order to complete a full oscillation. Okay? So if I take my angular velocity and I divide it by 2 pi, that will get me my oscillations per second, because it's radians per second divided by the total radians in one oscillation. So, as we can see here, the reciprocal of 1 over frequency is frequency, and the reciprocal of 2 pi over omega is omega over 2 pi, which exactly corresponds to what we just derived. Frequency is oscillations per second. So that's how the unit of angular velocity fits into this. Okay, now we have some dedicated equations that allow us to interpret the period of certain types of harmonic motion. The next equation on your reference sheet says T sub s, which is the period for a spring. The period for a spring system I have just illustrated for you here is equal to 2 pi times the rad of m over k. Okay? Where, of course, we know m is the mass of our object and k is the spring constant of the spring. Notice how in this equation, how long it takes our object to complete one oscillation has no reference to how far we pull it back. Okay? So we can pull this string out another like 6 inches and it'll continue to oscillate at the exact same speed. Oh no, I shouldn't say speed. It'll have a greater speed so that it completes one oscillation in the same amount of time, as if it would if I pulled it only 1 inch. But this derivation is important because we can combine it with this equation right here to say that the period equals this also equals 2 pi over omega. Okay? I got 2 pi on both sides, those cancel out, and I simplify to rad m over k equals 1 over omega, which can simplify to m over k equals 1 over omega squared, such that omega squared equals k over m. Okay? And that's going to fit into our differential equation derivation right here. If I divide both sides by mass, I get d squared x by dt squared equals negative k over m times x, which is something I've just derived out right here. So I replace the two, and I get the second derivative of position with respect to time gives me omega squared times negative x. And this is another form of the derived differential equation, which represents our harmonic motion here. Now, you won't be asked to solve this differential equation on the AP Physics C exam. If you've already taken a differential equations class in college, then it is quite possible that you will need to solve this. But for right now, we just need to know that the solution to this differential equation is the function of x that you are given on your reference table. Okay, you are given on your reference table that our x position, the position of our object in its oscillation, let me make sure everyone can see this, equals x max times cosine of omega t plus phi. Okay, and we're going to discuss exactly what this equation means. First of all, we need to acknowledge that there are multiple ways to illustrate this equation. Okay, so let me try and draw a graph of my position x on this example, the spring oscillating back and forth, okay? And it depends on my initial position, okay? If my initial position were at the equilibrium position, if my initial position were at the 0 position, then my graph would oscillate back and forth a little something like this, okay? Where in this case, if I start at 0, this would not be best represented with cosine. In fact, it would be best represented with sine. So you need to ask yourself, am I starting in the center? Or if I pull the spring towards one side and I release it from one extreme, then the graph would start at an extremum and then would continue to oscillate downward, such as this, okay? Where in this case, cosine would be best utilized to illustrate this. So you need to be cognizant of which trigonometric function you're using here. Also, the omega term can be replaced. As we have seen here, if I were to bring this equation down to demonstrate for you, 2 pi over omega equals 1 over f. Therefore, I can write f equals omega over 2 pi. And therefore omega equals 2 pi f. So if I wasn't given omega, if I wasn't given angular velocity and I was instead given frequency in my problem, I can use this substitution to rewrite my equation as 2 pi ft in this form. Okay, so let's discuss the rest of the terms in this equation. So we should realize why the cosine function is here, or the sine function in other examples, because we are dealing with oscillatory motion. And the sine and the cosine functions are functions that represent an oscillation, okay? Particularly, the sine and cosine functions continually oscillate between 1 and -1, okay? So in all of these harmonic motion problems, we're going to be defining the center point, the resting position of our spring, the position at which our spring is neither compressed nor stretched. We're going to define that position as 0, okay? So as we extend it further out, we're going to call that a positive displacement, and as the spring is compressed, we're going to call that a negative displacement. So as you can see, the mass, the block, is going to be oscillating between a positive value and a negative value, just as our cosine function demonstrates, okay? So x max, also known as A, the amplitude of our oscillation, is going to be the maximum distance it is displaced, okay? So if I were to pull the block 4 centimeters to the right, then the maximum displacement it will achieve is going to be 4 centimeters. So that means at its maximum displacement, cosine of this hullabaloo is going to be 1, so my maximum displacement is going to simplify to 4 centimeters. Okay, this term right here, the 2 pi ft, is a term that determines the speed of our oscillation, okay? So it's going to be a function of time. So as time increases, this multiple right here is going to determine how fast our oscillation progresses. And this phi this phi symbol right here. It's illustrated on your equation sheet to represent phase angle, but it's normally just interpreted as a sort of initial displacement, okay? So if you had your cosine of pi ft, your cosine function always starts at the extrema. Cosine function always starts at the maximum amplitude, okay? But instead, if I were to try and analyze this with a maximum amplitude at 4 centimeters, and I'm defining time equals 0 as representing this time when my mass is at 3 centimeters, then I would need to shift my cosine function to represent that. And that's where this phi comes into play. It's very rare that you would need to do a problem like that. Now, of course, here we should recall that our position function here obeys the kinematic differentiation rules that we learned previously, such that velocity is the derivative of position and acceleration is the derivative of velocity. So if we try to differentiate this, we're going to get the velocity of our block as a function of time. Let me make sure this marker is dark enough for everyone to see, is equal to our constant multiple x max, or amplitude. I prefer to write it as amplitude. Derivative of cosine is negative sine, multiplied by let's write it in the omega form. Omega t plus phi times the derivative of the inside, which is omega. Okay? And we can rewrite our acceleration as a function of time equals negative x max times the derivative of sine is cosine omega t plus phi times omega, which we're going to assume is a constant, and the derivative of the inside again would be omega, making this an omega squared. So now that we have a function for acceleration, we can then equate that to our acceleration differential equation here. We stated that the second derivative of position with respect to time, which is the same as acceleration, equals negative k over m times x, which equals mass. Acceleration equals force divided by mass, which equals kx over m, okay? Which is also equal to negative omega squared x, okay? So this might be a useful derivation for us to do when we're solving equations like this. Next, we have discussions of the energy of pendulums, okay? So there are two easy ways to discover the total energy in a pendulum, okay? When you are in your oscillation and the object is at one of the two extremes, the object is momentarily stationary. The object is not moving. Therefore, the entire energy of the system is in the form of spring potential energy. Okay? So at the instant of extremum, this is equal to negative k x squared over 2, where x squared in this case would be your x max, or your amplitude, which equals negative ka squared over 2. This is one way we can represent the total energy in a system, in the spring system, negative k times our amplitude squared over 2. Now, the other case we can consider is at the center point, at the 0 point, where there is 0 spring potential energy because the spring is not compressed or stretched from its equilibrium position, but rather all the energy is in the form of kinetic energy. So the energy sub tot is equal to the maximum kinetic energy, which is equal to 1/2 mv max squared. Therefore, if you're given the spring constant of the spring, the amplitude to which it is extended, and the mass of the object, you will be able to calculate its maximum velocity. Okay? Because we know that the total energy of a system is always equal to the total potential plus the total kinetic energy of a system. If you wanted to find the potential energy at any given point, you would just do 1/2 spring constant k times the displacement at that point squared. If you wanted to find the kinetic energy at any given point, you would do 1/2 m times v squared, and v, of course, is a function we just derived. That then brings us to our discussion of pendulums. Here is where we find a new type of pendulum that was not introduced in the previous years, so buckle up for that. First and foremost, we have the simple pendulum, which I'm sure many of us have seen in action before, okay? Simple pendulum would be, for example, a small mass being suspended from a string as such, and the mass is held straight down, you pull it a small angle theta, and you allow it to oscillate, like this. And as per usual, we ignore the effects of air resistance, okay? And it oscillates as such. The period for a pendulum hanging in such a way, T sub b equals 2 pi times the radical of the length of the string L over the gravitational constant G. If I were to draw a representation of this pendulum, and let's say I displaced the pendulum a small distance theta before allowing it to oscillate, so if I were to draw the free body diagram of the mass in the pendulum, and I were to define my axis as such, my axis being parallel with the tension force, draw my tension force in the string as such, and my gravitational force acting downward as such, okay? Therefore, if we resolve the gravitational force into components, we'll realize that the angle theta we make with the vertical is equal to this angle theta. Therefore, the component of the gravitational force that is restoring our pendulum back to the origin, the restoring force, is going to be equal to the force of gravity times this component of the gravitational force, which would be given by sine theta. Okay, that is our restoring force. So if we want to reconsult the differential equation, Fg equaling mg sine theta is equal to our restoring force. So g sine theta is our restoring acceleration, which is therefore going to be equal to d squared x dt squared, which is equal to our negative angular velocity times our displacement theta in this case, because we're displacing through theta, we're not displacing through x. Now we're going to consider what is the scenario when we don't use a string, when we use something that doesn't have negligible mass. So let's say we have a center point here, and we have a rod, like a solid metal rod, that is oscillating around that center axis of rotation, okay? In this case, you are dealing with rotational motion, okay? You have a center of mass. You have a moment of inertia for this situation. So if I draw my vertical in as such, I could draw the force of gravity acting on the center of mass of the rod, and of course that would be balanced by the normal force acting in the rod in the hinge right here. So again, I would say that my restoring force in this case would equal g mg sine theta. However, in this case, I'm not considering restoring force, I'm dealing with rotational motion. I need to consider restoring torque, which is going to equal my restoring force, mg sine theta, which is going to be in this direction, as derived, crossed with the radius vector. Now, the radius vector in this case is going to be exactly perpendicular, so the radius vector is going to be my length of the rod over 2, so that's going to be my restoring torque. So this term, of course, is just specific to this example, okay? This would be a general distance term which represents the distance from your axis of rotation to your center of mass. Your center of mass could be closer to one end or the other. It just represents this distance right here, okay? Now we can use the small angle approximation to state that sine of theta for very small theta is approximately equal to theta. Okay, therefore this can be rewritten for small theta as mg theta times our general length term d equals the restoring torque. Now, since we're not dealing with force anymore, we're dealing with torque, this can be rewritten in Newton's second law in rotational form, equals the rotational inertia I times the angular acceleration. Okay, I hope you guys can see this. My marker is running a little low on ink. I hope it helps that I'm narrating what I'm writing down as I'm doing it. Okay? Which brings us to the last equation on your equation sheet, the period, for a physical pendulum. That is what this is called, a physical pendulum, where this was a simple pendulum, is equal to, if I consult here, 2 pi times rad moment of inertia over mgd. That's going to be your period for the physical pendulum. Okay? And that should be about all we have for physicsy mechanics, guys. Again, if you have any questions, you need extra help, you need an extra cram session before your exam, I'm in the Discord server. I'm here to help you guys.